So, Happy New Year to you all, and welcome back to this SPSS session. I hope you are all doing well, and can kindly someone confirm if you can hear me? Kindly someone to confirm.
Perfect.
I hope that means you can hear me. Now, still more members are telling me that they'll be joining, but we can't wait that long. So, here today, we are supposed to discuss at least 2 subtopics, or rather 2 aspects. One, I remember that I had promised we will be discussing model building, where we will be building some model and all that. But I want us first to discuss about t-test before we can go ahead and try to build a model on regression analysis. We have done regression analysis, so it will be just a small aspect, or rather an element that we didn't discuss. So I want us to discuss t-test right from the beginning to the end. Everything about t-test, just a summary of everything. So some of us are hearing t-test for the first time, and some of us we are familiar with the t-test. So maybe before I say whatever I have to say, anyone who can tell us about t-test, like what you know about t-test, or rather there is a history even about t-test, or anything that you know about t-test. If you can't speak maybe from where you are, you can as well do that on the chat, so that I can read and members can see your opinion. So what do you understand about t-test? What is it that you know about t-test? I know most of us here have heard about t-test. We mentioned it when we were doing regression analysis, and we were trying to find the significance of the coefficients. And at one point we were saying we're using the t-test, say that if the significance of the t-test, the very same t-test. So what is this t-test? When is it used? And all that. Or anything that you know, even if it's a history. So I want us to understand t-test first before we do the analysis. It is quite important to understand, because you can't just do analysis. Maybe you'll end up doing the wrong analysis. So what is t-test? What is t-test? Anyone who can say something about t-test? You can raise up your hand if you have anything to say about t-test.
Hello.
Sorry. Yes, Lawrence.
I think for me, I can just make a trial.
Kindly go ahead.
Hello. Can you hear me?
Yes, we can hear you.
Yes, I think for my opinion, t-test is just used for comparison, to compare maybe a random sample. Maybe you've collected a sample from somewhere, maybe we can say like a population of somewhere, like we can say Mombasa County. So you use it to compare, for comparison between maybe the population. That's it.
Thank you very much, Mr. Lawrence, and that is a good attempt. That is actually true. Mr. Lawrence here is saying that we can use ttest to do some comparison, like we want to compare. Suppose we go to Mombasa County, and it was even specific. We get a sample of the population, and maybe we try to compare some aspect about that population based on the sample. That is ttest. That is very much okay, and that is correct. So any other opinion about ttest? Anything that you have about, you have heard about ttest, when it's used, or what do you know about it and all that? Ttest. Ttest. Now, because I'm a storyteller, I want to say this, that actually the T in the, it's ttest, not the T represents student. So this test was named after certain students. And what happened is that there was this one great chemist known as William Gosset. Now, the reason why I'm telling you this is where we start to understand the aspect of ttest. So this is the brief, like a brief history, not a history as such though. So what happened is that William Gosset was a chemist, if that word exists, and also a mathematician. And this guy was working for a Guinness brewing company. Now he developed the ttest in effort to track the quality of the beer that was being produced. So this guy is a chemist and a mathematician. He's working in this company, and they are producing Guinness. Now he wants to track the quality of the produce. Now in order to do that, he developed now the ttest. Now after developing the ttest that was helping him to keep track of the quality of the beer, he wished to publish this test actually, so that other statisticians and mathematicians and all us now, we can get to use, we can get it and use it. He had to actually use what we call a pseudonym to protect the property trade of the, to protect the company, that is, because you see, if he just published that way, the competitors could access it and actually know that this one is useful in tracking our product as well. So he didn't want to disclose that. So instead, he used pseudonym, to protect the priority of the trade secret. Now, in his publication, actually, he was helped by this one great statistician we have been talking about, that is the Karl Pearson. We have been talking about Karl Pearson correlation. So he assisted him, and he published under the names of the students or other students in what we call Biometrika. So the T, the letter T, was selected from the last letter in student. So you can say it's student. Now the last letter is T. So that letter T was now taken to represent the test. And that is how now t-test came into place, and also t-distribution. So basically, when we talk about t-test, we are talking about three types of tests, because t-test is divided into three, or rather we can say there are three types of t-tests. Number one, we have what we call the one sample t-test, we have the independent sample t-test, and lastly we have the paired sample t-test. Those are three: the one sample t-test, the independent sample t-test, the paired sample t-test. Now the question is when to use this particular test and when to use the other. That is the most important thing, because to run the procedure in SPSS is very simple, and we'll all see that. But now to determine when to use the test is now what at times confuses people. So I want us to discuss one by one as we are doing. And I want us to start with the very first, that is one sample t-test. Now, one sample t-test, in this case, it is used when we have data on a dependent variable from a single group, or rather a sample, and we wish now to determine whether the sample mean is statistically different from a known mean, or rather an assumed mean. This is what I mean, like the perfect example that Lawrence was putting, or rather was saying, like we want to measure maybe something about population in Mombasa, but now we are using a sample. That is one aspect. And to understand one sample t-test even better, I normally like this one example, or rather explanation, that I will borrow from one of the scholars in statistics I've met by the name Dr. Robert Kelly. Robert Kelly would say, and this was the example he was giving, was saying, we have this company in Kenya that is manufacturing alcohol. Now this company which is manufacturing alcohol, maybe one type of alcohol, I don't know any, but I'm assuming Guinness is alcohol. No, Tusker. No, which is which? Guinness or Tusker? Okay, let's say Tusker. So it's alcohol. It's alcoholic, that is. Now, in that table, that bottle, you realize there's that, paper, right? Written the ingredients and all that. I don't know the ingredients or the what. Now you realize, based on that bottle, it is reading that the alcohol content in that bottle, the 500 milliliter bottle, is 75%. Is 75%. Now, people who consume this alcohol, let's say at Nairobi City Council, or Nairobi City, that is, they are complaining that the alcohol content is actually less than or not 75%. Maybe the reason as to why they are saying that is because someone is taking 3 bottles but is still sober, like hazishiki. Hazishiki. So like they are claiming that the alcohol content in that 500 milliliter bottle is actually not 75% as indicated. So after having this claim, and it gets to the Kenya National Bureau of Standards, they decide now to test the claim if it is true that the alcohol content is not 75% as indicated. So what they'll do is they'll go to Nairobi City, collect a sample of Tusker, those bottles, now the 500 milliliters bottle, a number of them, of course not all of them, because we can't get all of them. So now we are getting a sample. Now from this sample, we go compute the mean. And then now we have to test if that mean computed from the sample is statistical different from 75% as it was indicated. Now in that case, we are using one sample t-test. And the reason is that we are having only one sample of alcohol, Tusker, very specific Tusker. We are picking the sample, we are computing the mean, and now we are trying to test if this mean is statistically significant. Statistical different from the 75% that was indicated. This reminds me, at one point I was explaining this to someone and would say, now, why should you do the test now that you have the sample, you have computed the mean, maybe you are getting the mean to be 66, and then they are claiming it's 75%. Why can't you just say it is not 75? But you see, this mean is from a sample. One was reading 66, another one 75, another one 80. You see, so we want to see if that variation now makes it different from the 75% we are mentioning. So that is one perfect example of one sample t-test. One sample t-test. Now another example that we're going to use in this session is what we call, a scenario where we want to assess the performance of students. Assuming I'm a mathematician, or rather a mathematics teacher teaching this class, or let's even assume this class of data science, data analysis, that is, you guys are taking SPSS. The other time I was also having other guys taking SPSS. So you guys, you are January intake. I had September intake. Now the average performance, assuming the average performance after doing an exam for the class that just graduated with SPSS, their average performance was 85. Now those students are claiming that their class was performing better than this class, and they had an average of 75. So I would wish to test if your average performance will be statistically different from 75%. In such a case, I will also use one sample t-test. So that is why I was saying one sample t-test is used when we have data on a dependent variable from a single group or a sample, and we wish to determine whether the sample mean is statistically different from the known or assumed population mean. That is one sample t-test, and I hope we have all understand that. Now, because of understand that, and I've been talking a lot, let's first import our data. I want us to import our data. Now I have opened the SPSS. I shared the data set on the group, on the WhatsApp group, and it will also be on the description for the case of YouTube you want to review and all that. You can basically double tap the data and it will open, or you can open your SPSS like this, then you come navigate to files, open data, and by default the file type is SPSS. The file type is SPSS. So I'll navigate to where I have stored my data. My data is on desktop and it is almond. So I'll open that data set. Oh, I've not shared my screen all along. I've not shared my screen. Okay, thank you for the reminder. So let me share my screen. I thought I shared my screen. So that is the data set. I hope we all have the data set. If you are not able to open the data set, kindly let us know. If you have a data set on SPSS, kindly type 1. If you have your data set on SPSS, kindly type 1, so that I see how many are ready to proceed. Just type 1. I have my data set, so I'll type 1. I see Elvis is ready. Morrison, Evelyn, Esther. That's nice. Saifa is having it also. Lawrence is also having the data set. Joseph, you all have the data set. That's nice. So if you have also understand the aspect of one sample t-test, like where we are using one sample t-test, kindly type 1 on the chat. Type 2 this time, so that I can get the difference. If you understand the case when to use one sample t-test, kindly just type 2, and if not, type 0. If you understand when to use one sample t-test, kindly type 2, and if not, type 0. We need to move on the same. Yes, Joseph 2, Lawrence 0, okay, Morrison 0, okay, Esther 0. Whoa, whoa. Now I'll repeat this. I was saying one sample t-test is used when we have data on a dependent variable from a single group. And now we want to determine whether the sample mean of this particular data is statistical different from the known or rather the assumed population mean. I was giving this example, but I want to use this example here. This, now that we have the data set, look at this score. This is statistics test. Now these students were performing. This is the performance. This is the performance of this student in this particular class. Now this is the class of 2023, and this is the performance. Now someone somewhere would say that these students are not performing as the class of last year. And I ask this person, why do you say so? And he's telling me that because the class of last year had a mean of 80. So this class is not performing any better than that of last year. So I need to test and see if actually this class is performing differently from that of last year. So the only possible way, now that I have the mean of the other class, is to test if the mean of this class now is statistical different from that of last year. That is one scenario. Now another scenario is the one I was giving. We have this company that is producing alcohol, and it is producing Tusker. The brand is Tusker. Now the company is saying that, according to the company, the alcohol content of a 500 milliliter bottle of Tusker is 75%. Now, people who take alcohol at the Nairobi city are saying that actually the percentage of alcohol content cannot be 75%. It's not 75%. Reason being, maybe these guys are taking 4 bottles, 5 bottles, and still they are not drunk. Like they are still sober. So now, we need to find out if actually the alcohol content, the average alcohol content, is not 75%. It's statistical different from 75%. We want to test that claim. So what we'll do as Kenya National Bureau of Standards, we'll go to Nairobi, collect some sample of bottles of Tusker, go and compute the average alcohol content. We examine a bottle after bottle. Then we come up with the average of the alcohol content. And thereafter, now we have the average of the sample. We test that if it's statistical different from what the company was indicating that was there, which is now 75%. So we are testing that. Now another last scenario that I can give, still now with this class that is taking statistics, I want to test if this class is performing, is doing good. Now we normally say that someone is doing good on average if he gets 50%. So on average we can say that this class is performing better if their average performance is 50 or greater than that. Now, I want to test the claim that the performance of these particular students is actually greater than or equal to 50. The average performance of these students is actually greater than or equal to 50. So what I'll do is, I'll compute the mean of these students and now test it if it is statistically significant, different from 50. If it is statistical greater than 50, and we'll conclude that this class is performing better. I know someone somewhere will be asking me, why should we do a test? Suppose we compute the mean of this and we get the mean is 80. Is there a need to even compare it with 50 and say that the class is doing better? Yes, there is a need. Someone will say there is no need because it is 50 and now the mean is 50 and now 50 is greater than, is 80 and now 80 is greater than 50. So by default, the class is performing better. No, that is not how we conclude. And the reason as to why we should do a test, I want to demonstrate this using this. Allow me to just open this Word document and I'll show you something. I remember I was showing you the other time. Just, I want you to understand this, why we should do the test. Why we should do the test. Why we should do this test. So just a minute. Now, I'm assuming this is the performance of this particular student. Let me assume this is the performance. Suppose we have these students. Let me just enlarge them. Now, these are the performance of the student. We have one scoring 10, the other one is scoring 20, and the other one is getting 100. So the question is, what is the average performance of this student? We have 10, we have 20, and we have 100. Now we divide that by 3, and we are getting it's about 43. Or let's say, just for the sake of making sense, we have 30 plus 20 plus, that is 150 divided by 3, that is 50. Right? So this is a class of 3 individuals. This is a class of 3 individuals. Now assuming there are many, but the score, this is how the score is distributed. Now when we compute the mean here, you realize it is 50. It is 50, I guess it's 50, right? Now, based on what we were saying that when the average performance is 50 or greater, the class is performing better or is doing good. Now look at this. A class of 3 having a mean of 50. Would you say that this class is performing better? Would you say that this class is performing better? One student is getting 100, the other one is getting 20, and the other one is getting 30. Now the average is 50. Would you say this class is performing better? No, you can't say that. And why? It is because despite that the mean is 50, but now the variation in performance is actually very wide. One is having 100 and the other one is having 20. So we need to do a test that now will consider the variation of these scores as well as we try to compare the mean to the 50, which is considered to be the baseline to say when the class is doing good or not. Now that test statistic is called the t-test. And in this case is one sample t-test because it is one sample t-test because we are only dealing with one group of people, the students that are doing statistics. Now you realize I didn't want even to do this, but now I think I'll have to just show the formula for the t-test, and you'll see the aspect. I'll just have to do it. So let me just do it now because I've started. This was not part of the session, but now you realize that the t-test, the formula for the one sample t-test, this is how we write it. We have, okay, the mean, that is x bar. Now I'm not saying x bar, let's just say x, but now it's the mean. Assuming that is the mean, then minus now the non-mean or the assumed mean, or rather the population mean, and then we divide by we divide by the square root of the square root of the standard deviation. Now you see I need to get the symbols and all that. I didn't want to do that in this class. But the thing is, here we are dividing by, okay, let me just write this in words. The square root of the standard deviation of the square root of the standard deviation STD over the mean, over the sample size N. So that is basically the t-test. Now when you look at this test, I don't want to bring this because it is quite confusing for some of us who are not doing statistics. But basically that is the formula. Now this is over, divided by. Now you can see we are having the mean. I said this is the mean. This one here, now we have computed the mean. And now this is the assumed mean or the population mean. So we are assuming it is 50. So that when we are getting a difference, something that is greater than 50, we conclude they are doing better. But now we are taking into consideration of the standard deviation. Now there is the aspect of variation in performance, and we are dividing that by the number of observation. So basically what I'm trying to say is for the independent one sample t-test, we use it when we have data on a dependent variable from a single group or a sample, and we wish now to determine whether the sample mean is statistically different from known or assumed population mean. It can be known or assumed population mean, like the case of the company producing alcohol. It was 75%. It was 75. So it was known. Now for the case of student performing better, we are assuming if they perform 50, then they are doing well. So that is one sample t-test. Maybe we do this, we illustrate this, and we will understand better. Now, for this statistical test, we have this class, and this is the performance of the students in this class. And we want to test if this class are performing better on average, if their average performance is greater than 50, or let's say their average performance is statistical different from 50, we actually don't know if this class is performing better or is doing good or not. So we are not saying they're doing good or they're doing bad, but we want to test if they are doing good or bad. And our threshold is the mean, that is 50, such that if they perform or their average performance is statistical different from 50 and it is greater than 50, then we say they are doing better. If not, their average is different from 50 and it is less than 50, we are saying they are not doing better. So that is what we want to test basically. Now we are using what we call the one sample t-test. Now in this case, maybe to also help you understand even better, we normally, to do this test, we normally come up with hypotheses, things that will assist better. So the statistical assessment is made by the mean of t-test. And the null hypothesis always assume the equivalence between the sample mean and the population parameter. I mean the population mean, that is. So in this case, we will say that the mean performance, or rather the average performance of these statistics students is equals to 50. That is now the null hypothesis. Now for the alternative hypothesis will be the average performance for these students is not equal to 50. Now you see, is not equal to 50, it is two-way. It can be less or it can be greater. So that when it is less than 50, we conclude that they are not performing well. And when it is greater than 50, we conclude that they are performing well. That is the case. Now we are saying it's two-tailed. It can be greater or less. I hope you are getting that. That is one thing that you also need to take note. Now, I was saying that the null hypothesis is the average performance of the student is equals to 50. And I was saying the alternative is the average performance of the student is not equal to 50. Now you see, that is in the aspect of mathematics or statistics, and you are writing it. But now in terms of putting it in words, I'd say for the null hypothesis, the average performance of the statistics students is not significantly different from 50. The average performance of students taking statistics is not statistical different from 50. Is not statistical different means it is equal. So it's the same thing that I was saying initially. And now the alternative hypothesis will be the average performance of the students taking statistics is statistical different from 50. So you see now the aspect is different from 50. Now let's do this practical. How do we do that? Now to do this, of course, from the main menu we go to analyze. And here now we were talking about means, the average. So analyze and then we compare mean. Now under compare mean, we select one sample t-test. It is one sample because we are dealing with one group, that is the statistics class of 2023. So you select one sample. Now selecting one sample and clicking one sample opens now the one sample t-test dialog window. That is it here. Now from here what we do, we move the variable to the test variables panel, this panel here. You see we have the variable lists here, they are listed here. So now we move that one variable that you want to test to the test variable. So you can double tap or you single tap and you move using the arrow. Now Down here we have the test value. Now here is where now we place the assumed mean or the known mean. So in this case, we are testing if the performance of this student, the average performance, is 50 or less, or not equal to 50. So the test value is 50. That is the now what we want to test, the average performance. That is our threshold, like our threshold we are using here. Now, of course, there are options here, just like in any other dialog window, where now we can see the 95% confidence level as the default. We leave it that way. We also have dealing with missing values. We are talking about this, and we are saying we exclude cases, analysis by analysis. We will leave it default. So we click continue, and it is taking us back to the main dialog window. So we can just click OK, and it generates the output. So one thing that you notice is that it will first do a summary statistics, just like the one we do when we run descriptive under descriptive analysis. So we have the number of observation as 25. We have the mean. Now the mean of this student is 79.68. The standard deviation is that, and the standard error as well is that. Now we have the table for the one sample t-test. This is the table, and you can see up here it's saying the testing value. Now this is the mean that we were testing if the performance of these students is statistical different from 50. So we have the t-test, and this is the t-value. Now this t-value here was computed by the formula I was showing you. We will just talk about the values, and then we talk about now the conclusion, the storytelling now. So this t-value here is obtained by, now it is positive. So we are taking this mean here, 79.68, the sample mean that is. Then we subtract 50. That is now the assumed mean. We then divide by the square root of the standard deviation divided by the number of observation, and we are getting this t-test. Now here we have degrees of freedom. Now basically degrees of freedom is the number of observation minus 1. And the reason as to why we are subtracting 1 is because we are estimating one parameter. Now we have the significant value. We have been talking about the significant value of the t-test. Now the mean difference here is the difference in mean of the sample mean and the pre-assumed mean here. And we have it here. Now the 95% confidence difference is now the 95% difference confidence for the mean difference, where the mean difference lies. Now one thing that you need to remember at the back of your mind is that we were testing based on the null hypothesis that the average performance of this student is not significantly different from 50, or rather is equals to 50. And the alternative hypothesis was the average performance of these students is significantly different from 50. That is not equals to 50. Now we look at the t-value and of course the significance of the t-value. Now the significance of the t-value is actually less than the 5% significant level. So we will therefore reject the null hypothesis. Now the null hypothesis is the one saying that the average performance of the student is not statistically significant is not significantly different from 50. So we are rejecting that, meaning we will conclude that the average performance of these students is significantly different from 0. So that will be our conclusion. We will conclude that the average performance of this student is significantly different from 0. I hope you're getting that. It's significantly different from 50. Is significantly different from 50. Because we are saying the null, the average performance is equals to 50. The alternative, the average performance is not equals to 50. So we are concluding that the average performance based on the significance of the t-test is not equals to 50. That is, it is significantly different from 50. I hope you're getting that. Now you can even go ahead and look at the mean. You can see the mean of the student is greater than what we were testing. So by the virtue that we are concluding that it is significantly different from 50, it shows that from the means now, it is showing that it is actually greater than 50 and not less. So we can conclude that this class is actually performing better than the previous class. First, we have concluded that it is not significantly different from 50. It is significantly different from 50. So, is it greater or less? We can now compare the means and we are saying this one is greater. So therefore we can now conclude confidently that this class is performing better based on that particular test. I don't know if I don't know if you guys understanding this. Guys, do you understand that? Kindly, if you understand, you can just type 1, and if not 0. I see Esther is saying yes, Joseph 1, Elvis 1, Lawrence 1, Safe 1, Morrison, yes, Morrison.
I have a small problem.
Yes.
We compare the T 21556.
Sorry?
Which figure we do a comparison with the T of 21556?
Oh, the T. The T here.
Yes.
Okay, I get your question.
I thought we are comparing the T with something.
Now, I hope Mr. Morrison is asking, because I didn't get that clear, but he's asking which value of T are we comparing with 21.556 so that we reach our conclusion. Now, actually in this case, I didn't use the T value itself in terms of comparing and making a conclusion. But the fact is that, and I remember saying this sometimes back, when we want to test a hypothesis and make a conclusion, there are 3 approaches. Number 1, like for this case, we can use the T value. Because this is the test statistics. So number 1, you can use the test statistics. 2, you can use the significance of the test statistics. And 3, you can use the confidence. the 95% confidence interval, or rather the confidence interval. Now, if we decide to use the t, the t test statistics, that is 21.556, we therefore need to go to what we call a statistical table, read the value of the t score from the table based on the 21 degrees of freedom and 5% significance level. Now we will get a t value from the t table, and we will compare that t value, this t value, the t test here, the t value we are getting here, with the one we obtained from the table, such that, because this is positive, if this t value we are getting here, we are computing and we are getting here, is greater than the one we are getting from a table, will therefore reject the null hypothesis. Otherwise, we'll fail to reject the null hypothesis. So that is when now we use the test statistics itself. We'll have to bring the aspect of the statistical table, and this case is the student t distribution, or rather t score. So you'll read that at 24 degrees of freedom and at 5% significance level. I don't know if we really need to do that, but we can do it if you insist right now, because I can get the table online and read that. But I don't have to go and find a table when I have the output like this. Why? Because I have the significant level, and it will give a decision rule that will be equal as using the test statistics itself. And the decision rule for the significance level is that we are comparing this significance value with 5% for this case. If it is less than 5%, we reject the null hypothesis. And in our case, it is actually less than 5%. So we therefore reject that the average performance is not statistical different from 50, and conclude that the average performance is statistical different from 50. So we can use this. Lastly, but equally important, is that we can actually use the confidence interval of the difference to compare, or rather to conclude about the hypothesis, to either reject or fail to reject the hypothesis. Now, how do we do that? We look at the confidence level such that if the confidence level contains a 0, we fail to reject the null hypothesis. Now in our case, it is starting from 26 to 32. So there is no 0 here. So we'll reject the null hypothesis. That is another approach that we can use.
Yes, you did.
Okay. So any other question or concern about one sample ttest? Any concern? Any point that is not clear? Anyway, So that is it about one sample t-test. I want us now to look at the second type of t-test, that is the independent sample t-test. Now this is simple to understand and all that, because independent sample t-test, from the word independent sample t-test, it's like we are having two samples which are independent, like one sample that is not affecting the other in terms of measurement of that particular variable of interest also. Now, independent sample t-test assesses whether the mean of two independent groups, which now these groups are measured as categorical independent variable, is significantly different from a quantitative measured dependent variable. I don't know if I'm bringing a lot of statistics in the explanation, but the thing is that the independent sample t-test assesses whether the mean of two independent groups, and now I'm saying these two independent groups are measured as categorical independent variable. So it's one variable, but now it's categorical. So it has groups, let's say two groups. But now we are trying to measure if it is different based on those two categories for a quantitative dependent variable. Let me give this example and you will understand even better. Now, on the same scenario, we were talking about student performance in statistics. Now, this statistics class, or now this time let's use mathematics class here. We have this maths score, and we have sex. Now, sex is gender. Sex is gender. And in this case, we can look at variable view to see what are the values here. And we have 1 for male and 2 for female. So sex is gender. And 1 is for male and 2 is for female. So these are two independent groups. These are two independent groups. Like being a male does not affect being a female, and being a female does not affect being a male. They are independent. Now, these are the math students, and this is their performance. So, we want to test if this performance for male and female is statistical different. That is what we want to test. We want to test if the performance for male is statistical different from that performance for female. In other words, we want to test the performance of males in mathematics if it is statistical different for the performance of female in mathematics. In the same class, doing the same math, same teacher, but now they are male and female. So we have an independent variable that is categorical, and these categories are independent. They don't affect one another. So there is no way the performance of males will affect the performance of female, and the performance of female affecting the performance of male, and vice versa, except for very, very fishy reasons, but there is no. So that is why I'm saying the independent sample t-test assesses whether the mean of two independent groups. Now the two independent groups here we're talking about is the gender, which is now measured as categorical independent variable. And we want to test the mean of these two independent groups if is significantly different for their performance in mathematics. Period. I think that is a perfect example. So I don't know if you understand when to use the independent t-test, the independent sample t-test. Two samples that now do not depend on each other on a certain quantitative measure. That is independent t-test, where it comes in place. So if you understand, if by that explanation you at least understand how we use t-test, kindly type 1, and if not, kindly type 0. If you understand that explanation on when to use independent sample t-test, kindly type 1, and if not, type 0. There is no need rushing to do the analysis if you don't understand. Now, Elvis, this is what I'm saying. We have males and females as on gender. Now we want to test if the performance for males is statistical different from that of female. The performance in mathematics for males is statistical different for that of female. Maybe someone was claiming that in that class, males are performing better than females. So we want to test the claim. Is their average performance statistical different? When they are, it means one is performing better than the other. That is what we want to test the claim. Now, one thing you need to take note is that, this performance for males and females, or rather the groups, that is male and female, are actually independent. Like they do not depend on each other. You being a male does not affect the female, and one being a female does not affect being a male and their performance as well. So they are independent categories. They do not depend on each other. Now, because they are independent categories and we want to test if their performance, their average performance, is statistical different. If it is statistical different, we therefore go for the independent sample t-test. And actually, just to mention, we have what we call the ANOVA test. It is also applicable at this point for the independent sample t-test. It is called one way between subject and ANOVA. This is the general case of independent sample t-test, and it is often used on instead of the independent sample t-test. We at times use the one way between subject and ANOVA. That is the next thing we need to discuss, ANOVA and ANCOVA. But basically, that is when now we are using the independent sample t-test. I don't know if Elvis, you are getting that now.
Yes, I'm getting.
Okay, nice. Now, before we even go to do the analysis and see if the average performance of mathematics here is statistical different from gender, based on gender, for males and females. One thing that you need to take note about is that the independent sample t-test, or rather the t-test, is based on assumptions. So actually, there is no need of us rushing to interpreting the results of the t-test if these assumptions are not met. If these assumptions do not hold, we don't have to rush to do the interpretation. So we need to understand these assumptions and how maybe to make them hold if possible, and if not, what is the alternative way of doing it or reading or interpreting the results. Now, one assumption about the independent sample t-test is that the observations are independent. These observations for the students are independent. Like we are saying, they are not depending either on gender, so they are independent. Now, one way normally to obtain, or rather to make them independent, is actually to do what we call general randomization procedure, where now the participants are randomly and independently assigned to treatment or other conditions on the levels of the independent variable. That is, like, I'm coming to that class because I'm doing 4 samples, so I'm coming to that class and I'm just collecting the student performance randomly. Like, give me your score, regardless of the gender. Give me your score, and all that. Then now I note down the gender. So we're saying generally the independent as an assumption can be achieved through explicitly randomization procedure, where now the participants are randomly and independently assigned to treatment conditions, or rather the levels of the independent variable. They are assigned to levels of the independent variable. Like, we just do it randomly and we will achieve what we call the independence as an assumption. Now, another assumption is that the dependent variable is normal distributed. This one, we are saying that this is the independent variable for this case. We are saying that that is the independent variable and this is the dependent variable, because we are claiming that the performance is based on the gender. So because we are saying it's statistical, it might be statistical different based on the gender, that is male for female. So this is like the dependent variable. So it has to be normal distributed. And we were saying this, that can be the normal distribution, or this test can be assumed by graphical examination of the distribution of the dependent variable. Like, we plot this, maybe we have a normal curve and all that, or rather through special tests of univariate normality test, or we can run a test to test the normality for this variable. We'll do that. Now, one important assumption that we will always check, because the other two in most of the cases they'll hold, but now this one is very, very important, is what we call the homogeneity of variance, or rather the equality of variance. Now, what does this mean? The variance of the dependent variable, this one now here, the variance of the independent variable should be comparable across the independent variable. It should be comparable across the independent variable. Now, in simple terms, even though this is not the correct way in statistics, but I want to make it very simple so that you can understand it, is that the variance between these two groups should be equal. That is the equality of variance. That is, this assumption is like we are saying that the variation in performance for male, the variation in performance of mathematics for male should be equal to that of female. That variation should be equal. That is now the homogeneity of variance. And this one is very important. The equality of variance assumption is also called the homogeneity of variance. And I repeat for the last time, is that the groups have comparable variability on the dependent variable. They have a comparable, their variable is almost equal for their performance, and this is the dependent variable. Now what you need to take note is that this assumption is tested by IBM SPSS by what we call the Levene test. The Levene test will be used to test the equality of variance. That is, the variance is not statistical different for these two groups on their performance. Is tested by what we call the Levene test. Now, the rule of the thumb is that if the Levene test is statistically significant, then we say the homogeneity of variance has been violated. Now, that assumption has been violated. If it is statistically significant, we will say that the assumption has been violated. And if now the Levene test is not statistically significant, we say that the assumption holds. That is very important. If the homogeneity assumption is, the Levene test is significant, then the homogeneity variance has been violated. And if the homogeneity assumption is violated, what's next? Now we use another standard t-test that we will be reading as we get the type 1 error. As we get the output. So if the homogeneity assumption is violated, we use the use of the standard t-test now is not appropriate. It is not appropriate if the homogeneity of variance does not hold. And I remember this statistical class would say it is not appropriate as it will increase the chances of making type 1 error. Now type 1 error is we fail to reject the null hypothesis when we are actually supposed to reject it. That is now what we call the type 1 error. Failing to reject the null hypothesis while you are actually supposed to reject it. So if the homogeneity of variance does not hold and we are using the standard t-test, now we are increasing this type of error. Now, the question is, what if the homogeneity of variance assumption does not hold? What do we do? Do we stop using the independent t-test? What we do is that we have an alternative t-test procedure that we are going to use, and the output will always be there as well. The alternative test procedure was actually introduced by one statistician known as Welch back then, and IBM SPSS will always give the output as well. So after getting that output, you check now, is the homogeneity of variance assumed or not? Then now you decide which one to use. So let's come back here and do our analysis and now see where do we read and where now we make the conclusion. Now, I want us to use this math test. This is math performance in term 1, and we have the sex or rather the gender. Now our example here is concerned with this performance in math test for male and female. So it is always good to come up with the hypothesis because it will guide you. And now, before you come up with the hypothesis, again, it is always good to come up with a claim. So we wish to test the claim whether there is a statistical difference in performance between males and female. That is the claim. So our null hypothesis will be there is no reliable difference in performance between male and female. And now for the alternative, we can say there is a reliable test score difference between males and female. So you see the null hypothesis will always have no in terms of statement. So there is no reliable test score difference between males and female, and the alternative is there is a reliable test score between males and female. Now to do that, of course, from the main menu, we go to analyze, then we go to compare means, and then we go to independent sample t-test. Now this now will produce the independent sample t-test dialog window that we can all see here. Now from this variable list where our variables are listed, we now move the math test here to the test variables panel, this one here. So you can double tap or you can single tap and use the arrow. And now this will be the dependent variable in our analysis. The dependent variable, the math performance item 1. Now, we next move sex into group variable panel to represent our independent variable. So we are taking sex to group variable to represent our independent variable. Now you notice one thing. There is a question mark in the parenthesis. You can see the question mark here in the parenthesis next to the sex. Now this will not automatically appear in IBM SPSS, and it is actually asking us to indicate the values or rather the codes for the group variable. So we need to define the groups that we have in our independent variable. So to accomplish this, we click define groups push button. And now here we have group 1 for male, we put 1 as it is coded from the values, and group 2 we put 2 for the females. So the two groups were coded as 1 and 2, and we have filled them as they are supposed to be. So clicking continue brings back to the independent sample dialog window. Now again, there are options here. You can click the option push button. It is giving us the confidence interval percentage. The reason as to why I normally do this is because it's not always that we'll use 95%. So depending on your significant level, you can adjust. And missing values, we talked about this, so exclude cases analysis by analysis. And we click continue. So then with that, we can just click OK, and this will give us our output. This will give us our desired output. So the table is very low. Maybe I try minimize this. Let me try minimize the window. Now, this is our output for the independent sample t-test. Now realize one thing, it is first giving us a descriptive analysis. Now this descriptive analysis is actually one like when we were doing split cases. Remember that? Under data here, and we were splitting file by gender, and then we were doing descriptive analysis. So it is giving us the descriptive analysis for male separate and for female separate. So that is what it's doing here. The t-test by default will give us that descriptive analysis separately. So you can see the average for female is 46, and that for male is 46.00, and for female is 46.15. 46.15. Now the question is these two statistical different? Now we are doing the t-test here. Now what you need to take note is that the first two columns here are for the Lavín test for testing equality of variance. The first two columns is for the Lavín test, and the Lavín test is given by the F statistics and the significant value. So before we even bother about the t-test here, we need to bother, or rather to be concerned about the Lavín test, because you can see here we actually have two different output. We have equal variance assumed and equal variance not assumed, and we have t-value, we have t-value, degrees of freedom, so there are two. Now the question is, which one are we supposed to read? Is it the first row, this one, or the second? Now to determine which one to use is based on the Lavín test here, and we were saying if the Lavín test is statistical significant, if the Lavín test is statistical significant, then the equality of variance assumption is violated. It does not hold. It does not hold. That is what we said. If it is statistical significant, then the homogeneity of variance has been violated. I want to give you a hint of this so that it doesn't confuse you. When it comes to this test, you always need to have the hypothesis at the back of your mind. They'll help you to make the right conclusion and to make the right decision as well. Even if it's an assumption like this one, it is equality of variance. So the null hypothesis will be the variance 1 is equal to the variance 2. The variance are not statistical different, so they are the same. Now the alternative is the variance are different, so they are not the same. So if it is statistical significant, it means that they are not the same. So it violates the assumption. If it is not statistical significant, it means they are the same, because we are failing to reject the null hypothesis. So the assumption holds. I don't know if you are getting that. Now looking at the significance of the Lavín test, is 0.5, which is actually, because it is 0.594, we can round off this, and it is nearly 6. So it is actually greater than 5%. Actually, it is greater than 5% without even rounding off. Now, because it is greater than the 95%, so it is not statistical significant, equality of variance assumption holds. Now, because the equality of variance assumption holds, we are going to use the first row in reading our t-values, or rather our interpreting our independent sample t-test. We are going to use the first row. Now, because we have seen that the assumption of equal variance holds, we'll come back and look at the t-value here. If you want to use the t-value, it's okay. If not, you will basically use the significant value here, as I have just used in the other example. Now, one thing you need to take note is that the t-value here is negative, because we are taking this this 46 here, the mean here, and then it is subtracted by this one here. Is subtracted by this one here, and giving a mean difference of this. Is giving a mean difference of this, and the standard error difference is this. So we are taking this, which is now negative, divided by this one, the standard error of difference, giving us the t-value, which is negative. Now, had we on that grouping, when we were now grouping, you remember there was those two question marks and we were defining the groups. Had we started with 2 for female, then 1, this column would have appeared first, then this second. So it will be now this one, 46.15 minus this. So it will be positive here. So it will be positive. Now divided by this, our t-value will be positive. But the fact is that, be it positive or negative, the value will still remain the same and the significance will be the same. So there is no any difference when you are defining your groups. Now the Levin test, the equality of variance assumption holds. Now I'm looking at the significance of the first t-value. Now from the first t-value we can see that the significant value is actually 0.94 or 0.95, which is actually greater than 5%. We therefore fail to reject the null hypothesis and conclude that there is no reliable difference in performance between males and females. There is no reliable difference in their performance. And you can even see from the means, it is almost equal. So there is no reliable difference in performance between males and females. There was no males and females for mathematics performance. We can actually try to rerun that using now this other mathematics. That was term 1 and this is term 2. And see if there is a significant difference in performance for males and females. So I'll just change this performance. I put the 1 for term 2. I leave everything as it is and I click OK. And now you can see the Levin test still holds because it is not significant here. So I'm reading the very first and the significant value is still greater than 5%. So we conclude that there is no significant difference in performance between males and females. For mathematics, that is in term 2. Again, I can even do it with the statistical, the statistics there. So I'll compare means independent. Now instead of mathematics performance, I'll do it with the statistics. And I click OK. And when I do, now you realize here one thing, that the significance of the Levin test is greater than 5%. So it's not statistical significant. So the assumption holds. The assumption holds. Now because the assumption holds, we are using the first row, and you can see the significance is actually 0.002, which is less than 5%. So we reject the null hypothesis in this case. And what do we conclude? We conclude that there is a reliable difference in performance between males and females. There is a significant difference in performance, in the performance of statistics between males and females. And you can even see the mean. You can even see the mean. For males is 75.8, for females is 73. So you can even conclude by saying, actually, females perform better with an average of 83.46 than male with an average of 75.58. So that is the independent sample t-test. That is the independent sample t-test. Any question, any point that is not clear, and if you understand, if you have any question, any query, just raise up your hand and I'll pick you up. If you understand, kindly type 1. If not, type 0 on independent sample t-test. Oh yes, I say James 1, Elvis 1, Lawrence 1, Star 1, The rest, Morrison, 1. Esther is very quiet today. That is okay. That is good. And that is awesome. So let's go to the last one. That is now what we call the paired sample t-test. The paired sample t-test. So when do we use paired sample t-test and all that? When do we use the paired sample t-test and all that? Now the paired sample t-test is somewhat a different way to analyze data arranged in what we call a Pearson correlation or simple regression design. You remember we were doing regression analysis and we were also doing correlation analysis. Now I want to use that example first to demonstrate the paired sample t-test. I want to use the very same example. Allow me to open that data set. I don't even know if, I'm not even sure if I have that data set. Oh yeah, it is in Excel file. So just allow me to open that data set before we proceed and come to this example. Because I'm saying the paired sample t-test is somewhat different, a different way of analyzing the data that is arranged to do Pearson correlation or maybe regression. Because you realize in such a case, we have two samples. Suppose we have two samples. You realize each case is associated with two scores. Okay, generally in paired sample t-test, you realize that each case, we are saying that each case is associated with two scores that may represent either a different variable or the same variable measured at two different points in time. That is why we are saying it is like correlation and regression, data that is for correlation and regression. Now I want to look at the two parts of this statement. We are saying each case in such a data set is associated with two scores. And now these two scores, they may represent either different variable or the same variable measured at two different points in time. Now let's look at this data we were using. We were looking at consumption and income. If there is an association between consumption and income, we were looking at that. Consumption and income. Now, when you look at this observation, the observation go in hand in hand. Says that the observation number 2 here for consumption goes with this income. This consumption goes with this particular income. This consumption goes with this income. This consumption goes with this income. There's no way this consumption will be associated with this point or that point. So they are pairwise. That is why we are saying each case is associated with a score that may represent either different variable. So this is a case where we have two different variables. But now the cases are observed at the same time and they are associated. Now in this case, we can actually use paired sample t-test to test if there is that association or probability of these two being associated. These two being associated because they are pairwise in terms of their measurements. That is now the first part of the statement. The other part is that they are saying, or the same variable now measured at two different points in time. Measured at two different points in time. Now look at this case. This is a hypothesized data. Actually, I generated this data. This one is the performance, the maths performance for student in term 1. And this is the maths performance for student in term 2. The very same students, because we have student ID. It is representing a unique student. So this student, whose ID is number 1, performed, this was his performance in term 1, and this is his performance in term 2. So it is for the very same student, but now at two instances, at two different points in time. So these two now are paired. They are the very same student, but now at two different points in time. So it could be, maybe in term 1 we had this particular teacher, we had Mr. Morrison teaching them. Now we have Mr. Elvis as the new teacher. So we are interested to know, is the performance of students different, or is the performance of students associated with the teacher? I mean, does changing the teacher bring that aspect? That is what we're trying to test. So each case is associated with two scores that may represent either different variables or the same variable measured at two different points in time. Now, we invoke the ttest when we're interested in the difference between the means of the two measures. So this time now we're not doing correlation, but we are interested to see if these students are performing better with the new teacher than when they have the other teacher. So for this case now we'll invoke the ttest because we are interested in the difference between the mean performance of the student. Now such an approach uses what we call the paired sample ttest because the two measures are linked, or they are paired for each other. They are linked or they are paired for each other. So in the other case, they are paired. That is consumption and income. They are paired. In this case, they are linked by the student. The very same student. So we'll be invoking the paired sample t-test. Now realize one thing. The more application of the paired sample t-test is, or the more applicable cases of the paired sample t-test is what we call the pre and post design to assess meaningful change that may have occurred on the dependent variable between two time periods. This is the most applicable part or other concept or other instances where now we want to assess any meaningful change that may have occurred for dependent variable between two time periods. Same people, but at different time instance in time varies. So again, like I said, for independent sample t-test, I was saying there is an alternative of what we call the one-way ANOVA, the one-way between subject and ANOVA. Now for paired t-test, it is also known as the repeated measure or the within subject or the within subject or the within subject ANOVA. So this within subject ANOVA is the more general procedure to use when dealing with such. But now the paired t-test, this paired t-test actually explicitly make use of the concept of correlation between the measures when we are dealing with the paired t-test. So without much ado, or rather, let's just do it practically. We want to test if there is statistical difference in performance based on the fact that we changed our teacher and we recorded the observation at two different instances, and we want now to test that. So here now, what is our interest? Our interest, or rather the question of interest, is whether there is a statistical significant, there's a statistical significant change in performance between the two time periods. So is there a significant change in performance between these two time periods? That is term 1 and term 2. Now, to do that, of course, we go to the main menu to select Analyze. Then we go to Compare Means and its paired sample t-test. Now we have selected our paired sample t-test. Now this now opens the main dialog window, of course, and here we have the variable list and the paired sample variables where we need to move our variables. So from the variable list on the left side here, we now move match performance in term 1 to the variable to the paired variables, and then we move match performance in term 2 also to the variable panel. Now from the options, of course, we have the options. You can see we still have the same 95% confidence interval, exclude cases. We can just leave it that way, and we click OK, Now when we do, we realize for this case of paired sample t-test, we number 1 have the statistics just like the one for split files, and we run a descriptive analysis. Now you can see we have the means and all that. Now one thing is that it will give us a paired sample correlation. That is why I was telling you the t-test is actually based on the correlation. So from the correlation you can see that we have a strong positive correlation of correlation coefficient value of 0.8 and its statistical significant. The correlation value is statistical significant. So coming to the independent sample paired sample t-test, you can see the mean difference. This is now the mean difference, and it is negative because we are taking the first one 46 minus 65. Here, do we put match performance in term 2 first? We will have the same value, but now it's positive. The standard deviation, we have been talking about this. The standard error mean 95% of the mean difference. Again, we have been talking about this, and of course the t-test. Now we are interested to look at the significance. Now you can see that the significance is 0.00, which is, guys, can you hear me? Can kindly someone confirm if you can hear me? Okay, someone is asking me kwani class imeisha, and I'm like, am I speaking alone? So we are saying that it is statistical significant, implying that there is a significance difference in performance there is a significant change in performance that occurred between the two time periods when we changed the teacher. There
Hello,
is
Prof.
a significant change. Sorry?
Wengine sijui ni peke yangu, sijui uliniacha, umeniacha mbali sana.
Umeachwa wapi Walter?
Hata mmeanalyze mi bado, so tunaenda kwa analyze alafu compare mi tunaenda kwa paired.
Paired, yeah.
So what are we pairing?
This is what we are doing. Just check on the screen. So we are moving these variables here. The maths performance to the paired variable. That is maths performance in term 1 and maths performance in term 2. They are the paired variables. And then we click OK. Well, are we together? Hello, Lawrence?
Yes, you're together. Thank
you. Okay. Now